It's resolved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.
Hello students, welcome to S. Chand Academy, official YouTube channel of S. Chand Publishing. The book which we are discussing here is JEE Mains and Advanced for Mathematics by ML Khanna sir, and I am giving you videos of this chapter exclusively to boost your preparation. The chapter which we will start now is the chapter Mathematical Induction. Last class we did permutation and combination. So let us see some basic theory of mathematical induction. It is a small chapter, not a big chapter. So there is a base step involved. What is that base step? That when we take any statement Pn and we say that Pn statement is true, we check it for n is equal to 1. If it is true for n is equal to 1, then we proceed further. We do induction hypothesis. What is the induction hypothesis? In induction hypothesis, we say that it is true for n is equal to k. Assume true. Now, after assuming true for n is equal to k, in induction step, we do the third step, which is the most important step, you can say. Prove Pn is true for n is equal to k plus 1, and if it is so, hence it is true for all n belonging to natural numbers. So this is the basic concept behind it. Let us see few questions so that we will see the application of this mathematical induction. So the first question which come to us is this one: 1 square plus 3 square plus 5 square so on plus 2n minus 1 whole square is 1 by 3n into 4n square minus 1. You have to prove it by induction. So for n is equal to 1, we will see left hand side. Left hand side is 1 square, which is 1, and we will see right hand side. Right hand side will be 1 by 3 into 1 into 4 into 1 square minus 1. This will be 3 by 3, 1. So it is true for n is equal to 1. Let us assume that it is true for n is equal to k. Let us assume. That means 1 square plus 3 square plus 5 square till 2k minus 1 whole square is equal to 1 by 3k into 4k square minus 1. It is true. Now for n is equal to k plus 1, we need to prove it. For n is equal to k plus 1, when we will prove it, we will say that left hand side is equal to 1 square plus 3 square plus 5 square so on 2k minus 1 whole square plus 2k plus 1 whole square. Now from first term to this kth term, it is already we have used the assumption this one. So by that we can say 1 by 3k into 4k square minus 1 plus 2k plus 1 whole square is a extra term. So this is equal to, now this can be written as 2k minus 1 into 2k plus 1, and 2k plus 1 can be taken common from both of them. So I am doing it in this next step, and here it will remain 1 by 3k into 2k minus 1, and here plus 2k plus 1. Now when you will take LCM, after taking 2k plus 1 common, what will happen? 2k square minus k plus 6k, that will be plus 5k after taking LCM and simplifying, plus 3, and 3 we can take outside 1 by 3. So this will become 1 by 3, 2k plus 1, and let us do the middle term splitting here. So this is 2k plus 3k, so 2k plus 1 plus into into this will become, after middle term splitting, 2k square, that is k plus 1, and this will become 2k plus 3, sorry, this will become 2k plus 3 and this will become k plus 1. Okay, you can multiply and check, 2k square plus 3k plus 2k, 5k, that will be plus 3. So this is becoming 1 by 3 k plus 1 into 2k plus 3 into 2k plus 1, which is 2k whole square, that will be 4k square plus 6k plus 2k plus 8k plus 3. This is 1 by 3 k plus 1, and further 4k square plus 8k plus 3 can be written as 4 k plus 1 whole square minus 1, like this. You can simplify and cross check, 4k square plus 8k plus 4 minus 1 is 3. So this is nothing but the right hand side of this expression when n is equal to k plus 1. This is the RHS for n is equal to k plus 1. So this is how you can prove this, right? Hence it is true for all n belonging to natural number, because for 1 it is true, for k we assumed it to be true, and for k plus 1 we have proved it to be true. Let us come to the next question. Square root of 2 plus square root of 2 plus square root of 2, so on, like this. And we keep on writing it like this up to n terms, and this is equal to 2 into cos pi by 2 to the power n plus 1, where n belonging to natural number. So first one, where n is equal to 1, left hand side will be root 2 and right hand side will be 2 cos pi by 4, that is 2 by root 2, that is root 2. So LHS is equal to RHS for n is equal to 1. Second, for n is equal to k, let us assume it is true. That is root over 2 plus root over 2 plus root over 2 plus dot 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 up to k terms is equal to 2 times cos of pi by 2 to the power k plus 1. Now, in the third step, we have to prove it for n is equal to k plus 1. So LHS will become root over 2 plus root over 2 plus dot 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 up to k plus 1 terms. Now, as you can see here, that from here to here there are k terms if you eliminate 1, 2 from outside, and for this value it is already given from induction hypothesis that this is 2 cos pi by 2 to the power k plus 1. So this is equal to, now 2 is taken outside as square root of 2, root over 1 plus cos theta. So we know 1 plus cos theta is equal to 2 cos square theta by 2. So using this you will write it as 2 cos square pi by 2 to the power k plus 2. So this will become 2 cos pi by 2 to the power k plus 2. What will be this? This will be the right hand side of the expression of the equation when n is equal to k plus 1. So this is equal to right hand side when n is equal to k plus 1. So this is how we can prove this for k plus 1. This means therefore it is true for all n belonging to natural number, as it is said. Explain the method of mathematical induction. We have already done in the theory, and use it to show that 11 to the power n plus 2 plus 12 to the power 2n plus 1, where n is natural number, is divisible by 133. So 11 to the power for n is equal to 1, when we will see 11 to the power 3 plus 12 to the power 3. So instead of calculating this whole number, let us use some formula. So this will be 11 plus 12 into 11 square minus 11 into 12 plus 12 square. This will be 11 plus 12, 23, and this will be 121 plus 144 minus 132. So this value will be 265 minus 132 to 133. So 23 into 133. Is this divisible by 133? Yes, this is divisible by 133 because it is a multiple of 133. Now for n is equal to k, I am taking it for n is equal to k. So for n is equal to k, 11 cube plus 12 cube, 11, no, for n is equal to k, it is not cube, instead of that it is something else. So for n is equal to k, it is 11 to the power k plus 2, 12 to the power 2k plus 1. This is divisible by 133. Suppose 133 m for some m belonging to positive integer. So for n is equal to k plus 1, what will happen? 11 to the power k plus 2 plus 12 to the power 2k plus 1. This is equal to. So I can write it as 11 to the power k plus 2 plus 12 to the power k plus 1. No, it will not be for k plus 1, it will be k plus 3, or this will be 2k plus 3 for n is equal to k plus 1. If you take n is equal to k plus 1 here and here, this is how it will become. Let me clarify here so that there is no doubt. This will become k plus 3, this will become 2k plus 3. So 11 to the power k plus 3 plus 12 to the power 2k plus 3, 12 square I am taking separately, and 12 to the power 2k plus 1, from here I am writing it as 133 m minus 11 to the power k plus 2. So this will become 11 to the power k plus 3 plus 144 into 133 m minus 144 into 11 to the power k plus 2. Now from here and here I can take 11 to the power k plus 2 common, and it will become 11 minus 144 plus 144 into 133 m. So this will become minus 133. So this will become minus 133. So 144 into 133 m minus 133 into 11 to the power k plus 2, which will be 133 taken common, 144 m minus 11 to the power k plus 2. So yes, this is divisible by 133. So we can say that this is also divisible by 133, and 144 m is greater than 11 to the power k plus 2. You need not prove that, but it is understood because m was a very big quantity from here. Next question on permutation on mathematical induction. Let p be a prime and m a positive integer. By mathematical induction on m or otherwise, prove that whenever r is an integer such that p does not divide r, p divides MPCR. So here the number is MPCR and p divides it. What is m? M is a positive integer, and you have to do induction on m. P does not divide r is an integer, and p is a prime number. So we will use these facts as we will come across. So for m is equal to 1, This will be PCR. Now, is PCR divided by P? So, what is PCR? P factorial upon R factorial into P minus R factorial. This can be written as, after dividing by P minus R factorial, P into P minus 1 into P minus 2, so on, P minus R plus 1 upon R, R minus 1, R minus 2 till 1. These are the R consecutive integers. These are also the R consecutive integers, and P is greater than equal to R. But not only it is greater than equal to R, we already know that P is greater than equal to R for PCR to be defined, but it is saying that P does not divide R. So, P is not equal to R because P does not divide R. In that case, P is actually greater than R. Now, if this P is greater than R and these are the R consecutive integers and these are the R consecutive integers, then they are completely divisible. Why? For example, I am not going into the theory of that. To make you understand, I am telling 6 into 5 into 4, 3 consecutive integers. 4 into 3 into 2, these are also 3 consecutive integers. Where P, which is 6, is greater than R, that is 4. Then they will be completely divisible, as this will be 120 and this will be 24, that is 5. So, this will always happen that if there are in numerator P R consecutive integers, in denominator there are R consecutive integers, and the numerator integer is greater than the denominator integer correspondingly, then it is completely divisible. So, we will say yes, PCR is divisible by R, okay, because it is an not by R, sorry, by P. Yes, P divides MPCR where M is equal to 1. Okay. Now, for M is equal to K, we assume it to be true. So, P divides KP CR. This is true. Next, we have M is equal to K plus 1. So, what about K plus 1 PCR? So, you will expand it, K plus 1 P factorial upon R factorial into K plus 1 P minus R factorial, and when you will proceed further, you can show that this is also divisible by P. So, I am not going into much detail of calculation, I am just giving you an overview. Now, let us come to the next question. If AI is between 0 and pi, AI is some angle between 0 to pi, for I, 1, 2 till n, these are different angles. Use mathematical induction to prove that sine A1 plus sine A2 till sine An is less than equal to n times sine A1, A2, An all in addition upon n, where n belonging to greater than equal to 1 is a natural number here. This is a natural number. You may use the fact that P sin x plus 1 minus P sin y is less than equal to sin Px plus 1 minus Py, where P is between 0 to 1 and x, y are between 0 to pi. So, here again for n is equal to 1, LHS is sin A1, which is less than equal to 1 into sin A1 by 1, which is true. Since they are equal, this inequality is true because it includes equality. N is equal to k, it is true. So, sin A1 plus A2, so on. Sorry, these are separate signs. Sin A1 plus sine a2 so on till sine an ak less than equal to k sine a1 plus a2 till ak upon k. This is true, assumed. So for n is equal to k plus 1, let us check sine a1 plus sine a2 plus dot 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 sine ak plus sine ak plus 1. Now from here to here, this is already from principle of mathematical induction, induction hypothesis, less than equal to k times sine a1 plus a2 till ak by k plus sine ak plus 1. Now this is equal to k, I am writing it as k plus 1 and I am saying it as k plus 1 in the denominator, k upon k plus 1 sine a1 plus a2 plus dot 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 ak by k, and sine ak plus 1 is less than equal to sine ak plus 1, that we already know. So this I am taking as right. So plus k plus 1 I am taking common, so 1 by k plus 1 sine ak plus 1, right. So I am multiplying and dividing by k plus 1 to the second term also. So k plus 1 and k plus 1. Now you can assume that this k by k plus 1 is p, then automatically 1 by k plus 1 will be 1 minus p, because their sum will be 1. You can just check k by k plus 1 plus 1 by k plus 1 is 1. So this p, that is also 1 minus p, and p is between 0 to 1 because k is less than k plus 1 and k is a positive number. So you can, by using this fact, say that this is less than equal to k plus 1 as it is multiplied with sine px, that is k by k plus 1 into a1 plus a2 till ak by k plus 1 minus py. So 1 minus p is 1 by k plus 1, y is ak plus 1, like this. Now this k and this k will cancel, and in the next step, or you say in the last step, this is less than equal to k plus 1 sine a1 plus a2 till ak plus 1 upon k plus 1, which we had to actually prove for n is equal to k plus 1. So this is true for all n belonging to natural number. Next question, if x is not a multiple of 2 pi, use mathematical induction to prove that cos x plus cos 2x so on till cos nx is equal to cos n plus 1 by 2x into sin nx by 2 divided by sin x by 2. So for n is equal to 1, again left hand side is cos x and right hand side is cos of 1 plus 1 by 2x into sin x by 2 upon sin x by 2. This gets cancelled. This is cos x. So left hand side and right hand side both is cos x here. For n is equal to k, we assume it to be true. So we assume it to be true. In that case, cos x plus cos 2x so on till cos kx is equal to cos k plus 1 by 2x into sine kx by 2 upon sine x by 2. So, in the next step, n is equal to k plus 1 cos x plus cos 2x dot cos kx plus cos k plus 1x is equal to. So, from here to here, from induction hypothesis only, we came to know that this term is equal to this. So, let us replace by that cos k plus 1 by 2x into sine kx by 2 by sine x by 2 plus cos k plus 1x. Now, let us take LCM. So, right. So, this will become, or instead of that, one thing we can do, we can write this cos k plus 1x as 2 cos square k plus 1x by 2 minus 1. This is how we can write it. And then we take LCM. So, minus 1 is separate, plus cos k plus 1 x by 2 is taken as common from both of them. So, what else we have is cos k plus 1 x by 2. So, this is 2 cos k plus 1 x by 2 into sine x by 2 after taking LCM plus sine kx by 2 upon sine x by 2, right. This is what we have got. Now, from here, this is minus 1 plus cos k plus 1 by 2x. Now, there is a formula of 2 sine a cos b, which is sine a plus b plus sine a minus b. So, sine a plus b will become k plus 1 by 2x plus x by 2. So, that will become k by 2 plus 1x plus sine a minus b will become sine kx by 2 with a minus sign. So, this will be a minus plus sine kx by 2 here upon sine x by 2, and these two will get cancelled. Okay. So, this will become minus 1 plus sine k by 2 plus 1x into cos k plus 1 by 2x upon sine x by 2. So, there is no space left, otherwise I would have completed this. So, you can similarly proceed, and you can see that for k plus 1 this will come out to be true. Let us come to the next question. For any natural number n, you have to prove this inequality. So, the inequality here is mod of sine nx is less than equal to n mod of sine x. So, for n is equal to 1, clearly mod of sine x is less than equal to 1 into mod of sine x. Now, for n is equal to k, we assume it to be true. So, mod of sine kx is less than equal to k mod of sine x. For n is equal to k plus 1, when we proceed, mod of sine k plus 1x is less than equal to, not right now less than equal to, right now it is equal to, later on I will come to next less than equal to, mod of sine kx into cos x plus cos kx into sin x, right. Now this is less than equal to mod of sin kx into cos x by property of mod plus mod of cos kx into sin x. Now this is equal to mod of sin kx into mod of cos x plus mod of cos kx into mod of sin x. Now we know that mod of cos x is less than equal to 1 and mod of cos x is also less than equal to 1. So this is mod of sin kx plus mod of sin x. Now mod of sin kx is less than equal to k mod of sin x. So this is k mod of sin x is greater plus mod of sin x, which is finally equal to less than equal to k plus 1 mod of sin x. Hence it is proved for n is equal to k plus 1 also. Using the principle of mathematical induction, prove that for all n belonging to n, if y is equal to cot inverse x, then yn, this is the nth derivative of y, minus 1 to the power n minus 1 factorial sin to the power ny into sin ny. So when we want to do this, so for the first derivative we check dy by dx, that will be 1 minus 1 by 1 plus x square. So what is this? This is minus 1 to the power 1, 1 minus 1 factorial of course, upon 1 plus x square is 1 plus cot square y, because from here cot y is equal to x. This is minus 1 to the power 1, 1 minus 1 factorial upon, now cot square y plus 1 is cosec square y. So this is cosec square y. In the next step, minus 1 to the power 1 into 1 minus 1 factorial, and cosec square y is sin square y. That can be written as sin to the power 1y into sin 1y. So yes, for the first derivative, this expression is true. So let us suppose for the kth derivative it is true, minus 1 to the power k minus 1 factorial sin to the power ky sin ky. Now in the next step, yk plus 1, so that is actually derivative of y to the with respect to k with respect to x, and this is dyk by dy into dy by dx. This first portion it is clear, that is derivative of yk, minus 1 to the power k, it is outside, it is constant, k minus 1 factorial, it is outside, it is constant, and derivative of yk with respect to y, product rule. So k cos to the power k minus 1 y into cos y into sin ky plus sin to the power ky into cos ky into k into dy by dx. So dy by dx is this minus 1 by 1 plus x square, this is dy by dx. So this will become minus from there, so minus 1 to the power k plus 1, k minus 1 factorial upon 1 plus x square is here, and here what we are getting, k common. What else common we are getting here? Right, this is k cos k minus 1 y. Oh, sorry, I did a careless mistake here. This is sin k minus 1 y into cos y sin ky. So sin to the power k minus 1 y is common. Rest remaining is sin ky cos y plus cos ky sin y. So that is sin k plus 1 y. Now 1 plus x square is cosec square y. On numerator it will become sin square y. So this is minus 1 to the power k plus 1 k factorial sine k plus 1y into sine to the power k plus 1y. So yes, finally the right hand side is proved for n is equal to k plus 1. Okay, next question is, using mathematical induction, prove that for every integer n greater than equal to 1, 3 to the power 2 to the power n minus 1 is divisible by 2 to the power n plus 2 but not by 2 to the power n plus 3. So for n is equal to 1, what is the situation? Let us see. 3 to the power 2 to the power 1 minus 1 will be 8. It is divisible by 2 to the power 1 plus 2, that is 8, not by 2 to the power 1 plus 3, 16. Okay, true. For n is equal to 2 also let us check for the safe side. 3 to the power 2 to the power 2 minus 1. So it will be 80 divisible by 2 to the power 1 plus 3, 2 plus 2, that is 16. Okay, not by, this is 2 plus 2, not by 2 to the power 2 plus 3, that is 32. One more thing which has been observed here, that 3 to the power 2 to the power k minus 1 is actually odd multiple of 2 to the power n plus 2. Like here it is 1 into 2 to the power 3, here it is 5 into 2 to the power 4. So this is odd. That is why it is also not divisible by 2 to the power n plus 3. Otherwise, if it was even, then it was divisible. So that is why it is divisible by 2 to the power n plus 2 but not by 2 to the power n plus 3. That simply means this is odd multiple of 2 to the power n plus 2. So 3 to the power 2 to the power k minus 1 is equal to, or we can take 1 on the right hand side. This is equal to 1 plus odd into 2 to the power k plus 2. This is also k plus 2, n is equal to k. Now we will use this in the next. N is equal to k plus 1. This will be 3 to the power 2 to the power k plus 1 minus 1. So now this we have to prove. So we can write it like this: 3 to the power 2 to the power k into 2 minus 1, or 3 to the power 2 to the power k square minus 1. Now this is given as 1 plus odd multiple of 2 to the power k plus 2. So square of this minus 1. Now when we will square, 1 plus odd square is odd only, odd 1 I can take, into 2 to the power 2k plus 2 plus 2 times of odd into 2 to the power k plus 2 minus 1. So these two get cancelled. So this is 2 to the power k plus 3 taken as common. So here it will be 2 to the power 2k plus 4. So what it will be given? Odd 1 into 2 to the power k plus 1. And another term 2 to the power k plus 3 taken common plus odd. So finally this can be simplified like this, which is actually some another odd O2. This is odd, this is also odd. This is even actually, because 2 to the power k plus 1 is multiplied to it. This is even and this is odd. So even plus odd is odd, 2 to the power k plus 3, which shows finally that for n is equal to k plus 1, it is divisible by 2 to the power k plus 3 but not by 2 to the power k plus 4, because odd multiple of 2 to the power k plus 3. So this is how we solve the questions of principle of mathematical induction. That's all for today's lecture. Thank you, students.